Chapter 4, Properties of Matter. As we start this PowerPoint, we see a log that's on fire, and that is a chemical reaction. The wood is burning, and you know it's a chemical reaction because you don't end up with wood. You started with wood, but when the fire is over, there's no more wood left. What you have is ash and charcoal. And we're going to see that's a key aspect of chemistry. When you do a chemical reaction, you end up with new substances which you did not begin with. All substances have a unique set of properties that are unique to it. No two substances have the exact same properties. These are the physical properties of the chemical. And the physical properties are any characteristic that can be determined without doing any chemistry. So anything that you can figure out about a chemical while still having the chemical counts as a physical property. What its color is. They say taste here, but never taste chemicals. That's a terrible idea. Odor, what does it smell like? State of matter, is it a solid, liquid, or a gas? Density, melting point, boiling point. Anything that you can figure out about a chemical while still having that chemical is a physical property. Chemical properties describe how a substance chemically reacts. And you have to do chemistry to figure this out. Does something burn? Well, you have to try. Does it burn or does it not burn? You have to try it out. Does it react with chlorine? You have to try. The only way we learn about chemical properties of a chemical is by doing chemistry. And so the chemical properties, you need to do chemistry to figure out if it's a chemical property, and therefore you will end up with substances that you did not start with. Here we have sodium and chlorine. In pure metallic sodium is a very soft metal. You can cut it and squish it with a plastic kitchen knife. And pure chlorine gas is a heavy greenish yellowish gas. They're both extremely reactive, and when they react, they form sodium chloride. This is an extremely violent chemical reaction, so we never do this in the lab, but this shows a chemical property of sodium. It will react with chlorine to produce sodium chloride, which is table salt. Here we see 6 different compounds: chlorine, water, sugar, acetic acid, and nitrogen dioxide and oxygen. And we see the colors, the odors, their physical states, their melting points, and their boiling points. Notice for sugar, there is nothing there there is nothing stated for boiling point because it decomposes. That's true with a lot of organic chemicals. As they approach their boiling point, they just completely decompose into black tar and are destroyed. So a lot of organic compounds don't actually make it to their boiling point and therefore don't have boiling points, and it's noted in the literature as they decompose. So for chemicals like that, we would have to do a vacuum distillation, where you use a strong vacuum pump to seriously lower atmospheric pressure so that you could boil it at a much lower temperature so that it would not decompose. Physical changes are changes in the physical properties or changes in the states of matter without a change in chemical composition. No new substances are formed during a physical change. So melting ice is a physical change. You start with H2O and you end with H2O. Chemically they're the same. But the difference is you started with solid H2O and you ended with liquid H2O. If we take that liquid water and boil it, now we have gaseous H2O, steam. That's another physical change. Chemically, it has not changed at all. Chemically, it's still exactly the same. It's still H2O. What we're changing are the physical states of it. Here we have a picture of someone sawing wood. That's a physical change. After you saw the wood, chemically it's still wood. It's just in smaller pieces. You've physically changed it, but you still have the exact same chemical as you started with. In a chemical change, new substances are formed. Here we have a picture. Copper does not typically react with oxygen gas, not at room temperature. And so here, if we use a blowtorch and we heat the copper metal up so hot that it's actually glowing red, now it will react with oxygen in the atmosphere, and we see black copper 2 oxide formed. Notice the triangle above the chemical arrow right here. That is the Greek letter delta, the capital Greek letter delta. Usually in science, when you run into this capital delta, It means the change in something, but this is an exception. In this particular instance, the capital letter delta above a chemical reaction arrow indicates a lot of heat was applied. So that's the blowtorch that you see there. So again, copper does not typically like to react with oxygen, but you can force it using extremely high temperatures. So here we see the rusting of iron. That's a chemical change. You start with iron, metal, and oxygen gas, and you end with iron oxides. You have iron 2 and iron 3 oxides that are produced, and then it's all iron 3 oxide after a while. Boiling of water is physical. You change the state, but you still have water. Burning of sulfur, that's chemical. You have sulfur and you end up with sulfur dioxide. Boiling of an egg. This one needs to be updated. We used to put it down as a chemical change because it was irreversible, but a few years ago a scientific lab actually took a boiled egg and worked it back into a raw egg. And so the boiling of an egg is actually a physical property or physical change and not a chemical change. So textbooks haven't been updated yet, but it is possible to take a boiled egg and get the raw egg back. And so it's a physical change, not a chemical change. Combustion of gasoline, that is a chemical change. You pump gasoline into your car, but at some point after you're done driving for a long time, there's no more gas in the car. It all left your car as waste gases, and there's no more gasoline, and you have to add more gasoline to the car. And so again, combustion of gasoline produces compounds besides gasoline, and they leave your car through the exhaust pipe. Digestion of food, this is a chemical change. And all the food that gets absorbed into your body, you end up breathing out as carbon dioxide. There's a chemical change there. Sawing of wood is physical. You start with wood, you end with wood. You just get wood in smaller pieces. Burning of wood, this is chemical because you start with wood, but at some point the wood's gone and you have charcoal and ash. And so you no longer have the same chemical bonds there. Heating of glass, this is physical. Hot glass and cold glass are both glass. Same chemical bonds, same chemical compositions. So which of these following is a physical change? Grinding a rock into powder? Yes, because you still have the same rock, just in much smaller pieces. If hydrogen and oxygen react to form water, we form a new substance. If a shovel rusts, you're forming a new substance, red iron oxide. Acid and base reacting to form water, chemical change, we have a new substance. Burning sugar, you get black charcoal, we have a new substance, that's a chemical change. Which of these is a chemical change? Lighting a match. You can only use the match once because then the phosphorus is oxidized to phosphate and it has no capacity to keep burning. Melting aspirin, you still have aspirin. Breaking a plate, you still have the same plate, just in more pieces. Boiling antifreeze, you still have ethylene glycol, the same chemical, it's just in the gas state now. Putting sugar into tea, you formed a mixture, but we can separate those out through physical means. A chemical equation is a chemical shorthand used to represent chemical reactions and chemical changes. So chemical equations are useful because all chemists, regardless of what language they speak or where they were trained, write the chemical equations exactly the same, and therefore chemistry is universal. Anyone who looks at it understands it. And here we see 2 molecules of water are decomposed into 2 molecules of hydrogen and 1 molecule of oxygen through electrolysis. On the left-hand side of the arrow, you'll always have your reactants. The reactants are what you started with. So reactants are what you start the reaction with. On the right hand, you get the products. So products are on the right hand of the arrow. And that is what you produce. They are things you do not start with, but that you produce in the chemical reaction. And the arrow means yields or produces. So in this case, we react water to yield or produce hydrogen gas and oxygen gas. Physical changes always accompany chemical changes because if you have a chemical change, you produce a brand new unique substance. And all substances have unique physical properties. And therefore, because you're making a new compound, that compound will have new physical properties. And therefore, there are physical property changes. Energy is the capacity of matter to do work. And the 2 major types are kinetic and potential. Kinetic is the energy that is in motion at that moment. Potential energy is stored for later use. And these types of energy can be mechanical, chemical, electrical, or nuclear. And again, potential energy is stored. So energy can be stored by position. Something higher up has more potential energy because gravity will bring it down. Energy can be stored electrically. In a capacitor, you have stored electrical energy. Energy can be stored in nuclear bonds. Then if you can break those bonds, like uranium fission, you can unleash that energy and use it to produce more electricity. Energy can be stored in mechanical systems, like a spring. A wound-up spring is stored mechanical energy. Energy is stored in chemicals all the time. Food is stored chemical energy, and when you eat that food, your body breaks those bonds and extracts that energy and does stuff with it. Or gasoline, the energy is in the carbon-hydrogen bonds. And your car is able to extract the energy out of those bonds and make the car move forward. So energy can be stored in these systems, or it can be used right now, which is kinetic energy. So again, kinetic energy is the energy of matter due to its motion. It's in motion. When water held by a dam is released, its potential energy is converted into kinetic energy, and that kinetic energy is typically used to spin a turbine to produce electricity. But if we think it all the way through, this is another form of solar energy, because now the water's all the way down here, but the sun is going to shine on the water, it'll evaporate, rain back down up higher, and go through this waterfall again and make more electricity. And so hydroelectric energy is actually another manifestation of solar energy. The calories used are actually from the sun. Because this is a zero waste way to produce electricity and there's no nuclear waste, this is one of the absolute best ways to produce energy because it is a relatively easy to implement solar powered system. In chemistry, energy is usually released as heat, and that's not an accident. Heat is the most disorganized, most random form of energy. So literally every other energy form can be used to make heat. You can always make heat. In physics, they call this the quality of energy. And different energies can produce all the qualities lower than it, but not the qualities higher than it. So heat is the lowest quality energy. All other energies can be used to produce heat. There are a small subset of reactions that produce visible light and chemoluminescence, like luminol, which is used at crime scenes looking for blood spatter, and also the reactions that you see in glow sticks, which light up. But most electromagnetic radiation that comes off of a chemical reaction will be infrared. Typically, it is heat that is lost in a chemical reaction.